All right, hello, welcome to my presentation. It's a whirlwind tour of quantum complexity theory. So there's really two things to cover. The first third of this is going to be an introduction um, tour of regular complexity theory, classical complexity theory, and then in the latter section we're going to sort of take everything we've seen there and translate it over into quantum. So the first question that you might reasonably have in a presentation like this is, what is complexity theory? Why do we care? So the field of complexity theory covers computational models, their relationships, computational problems and their relationships, and also this notion of the difficulty or complexity of solving a certain problem, sort of like what resources are needed in order to solve that problem. Okay, and again, why care about complexity theory? Well, as a programmer, it's very important to know what problems that you can't solve. And that's hard to figure out by guess and check, but with math, we can determine that there are problems that you can't solve or are unlikely to solve given some conjectures. As a theorist, complexity theory is also very interesting because it sort of allows you to outline the limits of computing. It also allows you to theorize about new types of machines and what they might add to the table in terms of what problems you can and can't solve. So now we'll go through sort of a complexity theory 101 in a few minutes. The first thing you need to do complexity theory is you need a model, a computational model. Most of the time this is some sort of Turing machine. So a Turing machine is in essence like the weakest possible computer that can still do everything that you would want, right? It's specified as like an infinite tape. This is a mathematical object after all, so this can be infinite. An infinite tape of symbols, you can think of these as bits. There's also a control block, which you can kind of think of as a running program that sort of knows about the program state, the internal state, like what line of code you're on, and this thing is allowed to slide along and back the tape, change the symbols, look at the symbols. In essence, the control block is the running program, and the tape is the memory, or the data of the program. Of course, you can go further in complexity theory. Half the fun is going further. You might consider augmenting your Turing machine, making it probabilistic, giving it access to randomness and asking what that does. You might make it non-deterministic. These are actually very powerful machines. We can't actually realize them. They're allowed to look at multiple paths at any branch point, any if-else, and select the best one, the one that is sort of correct in some sense. That's very strong, of course. And then there's other things you could look at, like circuit complexity, where you investigate logic gates instead of this Turing machine idea. So now that we've specified models, we need to specify the problems that they're trying to solve. And this is a little interesting because programmers are solving all sorts of problems. Sometimes you're doing search, sometimes you're validating or approximating something. In order for this to be tractable, complexity theorists usually pick one section and stay in it, and the standard one is the decision problem. You can look at the others certainly, but the decision problem is the gold standard. These are sort of like functions that return a Boolean in essence. It's going to take a string, as in general it's a string, and it's going to accept or reject based on whether this input has a certain characteristic. So you might look at the click problem. We'll mention this later. Actually, the click problem, which is a description of a graph and a number k, and it has to accept, or the machine should accept, if the graph has a click of a certain size. So that's a classic example of a decision problem. After you have this idea of how to specify problems, you want to begin to look at them and you want to begin to categorize them. And they are categorized based on what resources are required to solve the problem. So the important categories, here are kind of four of the most important categories. We have P, which is problems that can be solved in polynomial steps by a Turing machine, a normal Turing machine. There's NP, which is the same idea, but by a non-deterministic Turing machine. Then there's P space. This is problem solvable in a polynomial amount of space, no matter how much time is used. And there's exp time. This is problem solvable in an exponential number of steps, no matter how much space is used. So we see that we're kind of interleaving ideas of space and time and non-determinism here. As always, polynomial and exponential is always with respect to the size of the inputs, like the bits of the inputs. And it's all asymptotic too, right? We also have relationships between these classes. This is the next thing to look at. You have this inclusion diagram for these four basic classes. This is taken from CIPSR. We have P is in NP for sure. NP is in P space, and P space is in exp time. And of course, there are actually many, many, many more classes, and they all have relationships, and some relationships are more complicated than the sort of linear one we have here. But that's all well and good. Okay, so then it's not a good introduction to complexity theory if I don't mention the sort of glaring open questions in this field. The most famous one being P equals NP, which asks whether or not P and NP are the same set of problems. The consensus is no, but we don't truly have a proof for this. We would really like one. Similarly, the other classes on that diagram, actually, we don't even know their exact relationships either. We know the inclusions, but we don't know if P and P space are equal, or if NP and P space for that matter. We also don't know if P space and EXP time are equal. So these are also challenges. It seems it's easier to state a problem in complexity theory than to answer it. Okay, so we're going to take all of that. We're basically going to go down that process again, except instead of classical, we're going to do quantum complexity theory. So again, let's do a sanity check first and see why would you want to do it. And it's sort of for the same reason you want to do classical complexity theory, except I think it's a little more compelling actually for quantum. We really want to know the boundaries of quantum computing because we want to determine if it's worthwhile to develop this. We want to determine, we'd really like to see that quantum gives an advantage over classical computing, that this is worth doing. And we'd also like to see sort of how far that advantage extends. Okay, so we're going to begin the process. So first you need to specify a model. And a natural thing to try to do here is to take your standard Turing machine and you're just going to upgrade it into a quantum Turing machine. And you can kind of imagine how that would work, right? A normal computer uses bits, a quantum computer uses qubits. So the idea here is we're going to take the tape of the Turing machine and replace it with a tape that's allowed to be in superposition. So it feels like it's made out of qubits in some sense. Interestingly, we also let the state of the Turing machine, this is the head or the control of the Turing machine, is also allowed to be in a superposition. All these superpositions are allowed to entangle. In fact, the state and the tape can become entangled to each other. And there you go. So yeah, it's like replacing bits with qubits is how you perform this transformation. A fully rigorous definition is available elsewhere. We don't have time to pick through it. It has some wrinkles to it involving reversibility and so on. We don't want to make this model too powerful, right? It needs to be something that could be realized in some sense. Now you might think that this model is too complicated, even though it's kind of the first thing to try to do. And you might be right. In particular, the idea that the head or the program, like the actual what instruction you're on, can be in superposition is a little concerning because we've been working with circuits where sort of the instructions are fixed and the operations are quantum. So one thing you can do there actually is do a circuit model. So we had classical circuits in complexity theory, so it's pretty easy to upgrade them into quantum circuits. It's exactly what you'd think. A solution, algorithm is given as a circuit. You feed in the input as the qubits that go in, and it puts its output as a qubit which is measured, where 1 means accept and 0 means reject. You do run into an issue when you do this, though. These circuits they can't be analyzed, because if you have a given circuit with fixed input size, as a circuit is specified with an input size, then technically that circuit has O of 1. It doesn't scale in size at all. It can solve all of its inputs in O of 1, which is a constant number of gates. So how do you fix this? How do you fix this? You want to look at circuit families, uniform circuit families in particular. So a circuit family is just like one circuit per input size. This way we can now, again, study how circuits scale as we change the size. So is it linear, polynomial, exponential, and so on. It's also really, really important that these circuits are uniform. So it's not enough that these circuits exist. We have to be able to find them. In particular, the way we specify this is kind of funny. We had to let a Turing machine, a classical one, spend a polynomial amount of time thinking before it spits out a polynomial size circuit. The poly time for the Turing machine bounds the time for the circuit. So I would like to say that this analogy is closer to like something like Qiskit than to an actual pure circuit, because it is a mixture of classical and quantum, right? It's exactly what Qiskit does, where it's classical code that builds a circuit and then runs a circuit on a quantum computer. So it's really nice that complexity theory is able to model something that complex so naturally. Luckily, I just said there are two models. You might worry, are they different? In reality, they're equivalent, right? They're different, yes, but they can solve the same set of problems, which is all that complexity theory cares about. So we're free to swap back and forth as is convenient for us. And so we will pick the circuit model because that's clearly more comfortable to us. Okay, so after we state our models, we'd like to start classifying problems. So let's state a class. This class is called BQP. It's sort of the most important quantum complexity class. It's loosely analogous to P, sort of the class of problems that we can actually feasibly solve in a classical computer. BQP stands for bounded error quantum polytime, polynomial time. Which is a mouthful, of course. So let's unpack that. It's a problem or problems in BQP if it is decidable by one of these uniform families of circuits that is generated in polynomial time by a normal Turing machine. One interesting thing with the bounded error idea is that we allow the machine to be wrong. It's okay for it to be wrong a third of the time. Actually, this third value is arbitrary, but it needs to be less than half the time. And that's a little concerning. So I did dig into this to figure out why do we allow error. In practice, part of the idea for this is a lot of quantum algorithms like Grover's algorithm do run with a certain, usually very small amount of error. And ultimately, this is because like qubits are these inherently probabilistic creatures. So it's pretty comfortable to want to think of the entire machine as operating with success probability. If you are worried, if you do worry about this 1/3 error probability, then do know that there is a sort of standard trick in complexity theory, which is to repeat this algorithm so many times and take the majority vote, with the idea being that if you have 2/3 chance of success, then you have actually an even higher chance that like 100 runs of the algorithm is going to be a majority. There's some like law of large numbers that causes that to happen. Okay, so there's our main complexity class. There are more, of course, but we can't get into all of them. So now we're going to begin discussing the search for specific BQP problems. In fact, we want a specific type of the complete problems for this class. A complete problem is one that A, lives in the class, and B, is no easier than, in air quotes, other problems in the class. Specifically meaning that if you can solve the complete problem, you can solve the whole class. We sort of shrink it down into a single or even an equivalence class of complete problems. So click, which we mentioned earlier, is complete for NP. This means if we ever find a polytime algorithm for click, then we would have P equals NP, and that famous conjecture would be proven true. Actually, the conjecture mostly goes the other way, so we would be disproving it. Demonstrating a complete problem for BQP is closely related to the idea of quantum advantage, right? We want a summary of sort of how powerful BQP is, and a single problem that expresses that would go a long way. Ideally, we would find a nice BQP complete problem, or even a normal BQP problem that's not complete, and show that P cannot solve it, like normal Turing machines cannot solve it, and then that would have been quantum advantage, at least on the theory side. Okay, so I've sort of stated as if we don't have these. I was a little surprised to find that we do. We have one called a Prox-Q circuit prob. This is a very technical one, although I will state it. In essence, this is a problem that asks a machine, not necessarily a quantum one, to simulate a quantum computer, right? You get the circuit, and then we're trying to sort of determine what the computer will do, right? On a sort of fixed input. I believe it's like all zero input. You get two real numbers, alpha and beta, and you're asked to determine if the first qubit after the circuit runs measures as a 1 with probability less than alpha or greater than beta. And you also get a freebie, like it's actually not in between there. So you do get some wiggle room in some sense. It's not at all a surprise that this problem is BQP complete, because you can just like run this on a quantum computer, possibly a couple of times or with a slight modification. And you will, solve it instantly. Despite this, the problem is actually still very useful for relating BQP to other complexity classes. It's an upper bound on the difficulty of any problem in BQP because it is complete. Okay, so is that sort of problem a cop-out, right? It's kind of silly to say that, the hardest problem in quantum is simulating quantum computers. I mean, perhaps it's true, but it would be a little disappointing if that's the only thing quantum computers are good at, right? Luckily, there are more BQP problems that feel less synthetic, that are a bit more natural or like kind of useful, right? One example, which is hard to state, it's very like linear algebra based, is this local Hamiltonian minimum eigenvalue. It has to do with finding the smallest eigenvalue or estimating it for a certain type of matrix. And the trick is more or less like this is the type of matrix that quantum operations are specified as. So it is sort of inherently a quantum question, but it is taken out of the language of like simulate a quantum circuit. It's a bit more obviously useful. which is good. And there are a few more of these, so this is far from the only one. And we suspect there are many more, but we only know so many. Okay, so we've stated what BQP is. We have sort of a vague idea of like what lives within it. The last thing we'll talk about is how does it relate to other classes, right? The following relationships are quickly proved, right? We have that P is in BQP. Why? Because if you take a quantum Turing machine, you can just have it never create superpositions, right? And maybe if you had circuits, you can just like never use the H-gate or never use superposition. And you would essentially get behavior that can simulate a normal Turing machine. You may need so many ancilla bits in reality to do reversibility, but if the length of the computation is polynomial, then that's actually not a problem. In complexity theory, of course. We also have BPP. This is the class of bounded error probabilistic polytime problems. So this is very similar to BQP with this bounded error idea. We also give BPP the random coin mentioned earlier. This is also BQP for the same reason. BQP can just simulate this computer. If it ever needs to do a random coin flip, then all it does is it it puts a single qubit through an H-gate, and then it measures it to get your bit. Okay, and then so this bounds it from below. This tells you what's inside BQP. This kind of tells you like the easy problems it can solve. Let's figure out the limit of how hard it can get. Like, we would like to put an upper bound on that in particular. So an upper bound is EXP time, right? And what's the proof of this? Well, that's just our Lab 5 Python simulators prove that. A quantum circuit can be simulated by looking at the state vector and putting it through all the gates one by one in an exponential number of classical steps, in particular because that state vector is exponentially large. There are more interesting results. I'll go through one. I found this pretty interesting, which is actually, even though in some sense the state of a quantum machine, right, the state vector contains an exponential amount of information, and that if you write it all down, it's exponentially long. It's actually possible to do any BQP problem in p-space. BQP is in p-space. The trick of this is to sort of view it not as a sort of step-by-step computation, but like this computation tree. It does feel like you're looking at parallel universes again, even though we know that that's an oversimplification or even a sci-fi idea. The idea is you're going to, instead of going down the tree and looking at the whole thing at once, or even a whole layer at once, because those become exponentially large, you're going to sort of snake down. Do we have a mouse? You can snake down a single branch, since the computation lasts polytime. This is a polynomial number of things to look at. You can look at a single branch and you can sort of accumulate, you can just add the probabilities of all these end states together. And if you do this overall, you can learn characteristics of the actual final state, like in particular what the first bit is. So this sum of histories idea is pretty cool. Yeah, so that's how we know BQP is in p-space. Okay, and then, this, I think last slide, no, there's second to last slide. We have a fuller picture. This shows BQP in relation to a bunch of classes. So again, this is certainly not all of them. In fact, it doesn't even show EXP time. But we can show any arrow here, like B is included in BPP because of this arrow. It's included in P and so on. So you can see that BQP lives a bit above P, which is what we can efficiently do. We can efficiently do BPP as well. We can't do anything across this line. As far as we can tell, right? I mean, maybe with a very small input size, you can do some of these things. QMA is another quantum class that I wanted to throw in there. It's sort of our generalization of NP. So like P is to NP as BQP is to QMA. I won't go further than that, but it is interesting to know that such a thing exists. We also have this class PP, which is the another probabilistic class where we don't require bounded error. And it's actually very interesting that this can do anything quantum, at least anything in these two quantum classes, without even having a qubit. Of course, the class PP, these problems are very hard actually, because having like only a slightly more correct algorithm than incorrect, this doesn't give you a lot of confidence that you can ever even boost and run it many times and get a good idea statistically. Still, it's certainly very interesting. Okay, so this last slide, I believe, is about the open problems. So I wanted to emphasize what we do know and what we don't know about BQP, and this is what we don't know, right? We don't know if BQP and P are different, right? We certainly hope so. We certainly think so. This would be sort of finishing the project of quantum advantage would be to find a problem and prove that it's not in P and prove that it is in BQP and make them different. Um, and still, this is an unknown. I would call this sort of the big open problem for quantum complexity theory. There's more, of course. So you might wonder how BQP relates to NP. Like, can we solve NP problems with it? As far as we know, the answer is like probably not. We don't believe that BQP contains NP, so the NP complete problems in particular cannot be solved in a quantum machine. We're also unsure about the other direction, so maybe in some ways BQP is both stronger and weaker than NP. Ultimately, we just don't know. Um, Okay, that's all I have to say on quantum complexity theory, at least in this limited time. I see that I went a bit over. Um, I do find that this intersection of these fields is very interesting, and it does have some issues right now because our quantum machines are still very small. So saying things like, oh, you can do this in a polynomial number of qubits, well, that doesn't feel very realistic right now when it feels like we have more of a constant number of qubits, but they are growing over time. So perhaps someday quantum complexity theory will give an accurate picture. So it gives an accurate picture of where we're going, perhaps not where we are. Um, okay, that's all I have to say.